This video about the last man who visited and walked on the moon. NASA did the moonshot in 1972. Unbelievable, true? With the Artemis program, NASA will land the first woman and next man on the moon pretty soon, using innovative technology to explore more of the lunar surface than ever before. The aim of D2M project in moonshot trajectory is to explore and develop various state-of-the-art technologies for the production of carbon monoxide as a platform chemicals via conversion of carbon dioxide. Nothing is impossible.
Good afternoon, everyone. My name is Steve Nolan, and I will be discussing briefly advances made in our first work package, homogeneous catalysis for CO2 to CO conversion. So the first emphasis and efforts of this project have really been aimed at synthesizing in a simple manner a whole variety of different compounds that could be used to purpose. So we've developed easy ways to circumvent the very difficult ways to get to metal catalysts containing N-heterocyclic carbene ligand of this architecture or motif. So we've done away with strong bases altogether. We've done away with transmetallation routes. And what we do use now is our green routes using acetone and weak bases that enable you to get from the starting materials in the presence of a gold source to the final product used in the catalytic studies. So we've validated this route for a variety of different architectures in terms of supporting ligands. So this is a triazole that is also validated, and we have X-ray structures of these beautiful compounds. Reports have been published already in the latter part of 2020. So the method also works for derivatization of these compounds to make metal carbon and metal sulfur entities. So also we've published in 2020 this method. So these entities are specifically important as CO2 can possibly react with them. We've extended the method to other metals. So one metal of interest for this purpose of CO2 reduction is palladium. So here's a nice example of a palladium using a weak base assembly strategy using a palladium precursor triethylamines base in the green solvent acetone. We've extended further to the methods further to other metals. Here's a platinum example, very simply assembled in one pot. Essentially, we've identified an intermediate along the course of the reaction, so we know how this reaction proceeds, also published in the later part of 2020. For gold, we can form gold carbon compounds very easily by using a boronic acid. So the previous way to do that was horrendous in terms of synthetic approach. This article in the Chemistry European Journal has been highlighted as a very important or hot article. So we can essentially do things in air now, doing just phase cuts and separate the material, and we get nice white materials at the end. So we can have access to a variety of different architectures containing golden bonds. We've moved this synthesis into flow to go even faster now, and in collaboration with the Stevens group, we have very effectively made copper, another metal that we're extremely interested in for carbon dioxide reduction, palladium, and the gold compounds I've been telling you about. Again, we're developing very sustainable routes, but now these reaction times, as you can see, are cut down dramatically to essentially occurring in 2 minutes. Okay, so now we can really generate huge libraries and very, very, very short reaction times. Okay, so what have we done so far in the first few months of this project is really to synthesize a whole variety of different complexes, and for that we've actually developed a new route to get to a lot of compounds in a very short amount of time. We're interested in creating metal carbon bonds because I think this will be disruptors in derivatizing and reducing carbon dioxide. So we've made metal aryl, metal alkynyl as pre-catalysts for the functionalization of carbon dioxide, and now reactivity studies with carbon dioxide are next, now that we've amassed a number of catalysts for testing. Okay, so that's it in a nutshell. I really thank you for your attention, and really thank everybody for, especially the Moonshot, for the funding. Okay, so thank you very much.
Hi, welcome to Work Package 2. My name is Michiel Dusselier from KU Leuven, and in Work Package 2 we have collaborated with Professor Mark Sijs group in Ghent. So we've looked at heterogeneous catalytic approaches for CO2 to CO, but we decided to couple it to propane dehydrogenation. Why couple it? Well, propane dehydrogenation makes hydrogen, which can then be the in situ source for your CO2 reduction to CO. There are some benefits to this. For instance, if you look here at the right, you have the equilibrium conversion of propane in the classic PDH. If you add CO2, you see that the conversion of propane can be boosted. And in light blue, the conversion of CO2 can still be sizable. However, there's another mechanism, which is maybe even more interesting, the direct mechanism of coupling these two, where CO2 is activated on the same surface where your PDH has happened, and your CO is produced in situ. In that case, in red, you have a bit lower propane conversion, but a higher CO2 conversion on the same line, which can be interesting, of course, from a CO2 consumption point of view. Of course, we performed some life cycle assessments to see whether this really holds potential. So for instance, here we have compared PDH without any CO2 versus propylene made from FCC, and we see that this already has some benefits in terms of less emissions. However, if we then look at the coupling, the light blue one, or even the direct coupling, the red one, we see that we have a clear reduction of environmental impact, and it looks like there are much lower emissions if you would make propylene in this way and your CO as well. So this is quite promising. Especially if you look at these numbers of greenhouse gas equivalents per functional unit of propylene. But of course, to get to these conversions, equilibrium conversions, we need some catalysts. In Leuven, we have tested over 70 catalytic materials with about 20 different metals and metals oxides on a range of different supports. Typically, we express our data like this one, as you can see here for chromium oxide on alumina. We start with a 1-to-1 ratio of propane and CO2. And we ramp up the temperature during the plug flow regime, and we see that the activity starts to really boost at, let's say, 550 degrees Celsius, and we have a lot of different reactions happening. To interpret these plots, for instance, for these other oxides as well, we go to these types of figures. Here you can really see reaction selectivities. So reaction selectivities are the colors. In light green, you have propane to propylene. You can see at high temperatures during the temperature ramp. You also have some coking, there is some cracking happening, and some reforming at higher temperatures. We found the classic behavior for chromium oxide on aluminum, of course, which actually converts a lot of propane, but just a little bit of CO2, which points to this indirect mechanism of coupling. What we have interestingly discovered some other metals and metal oxides on alumina, which are capable of converting, let's say, more or less a 1-to-1 propane and CO2 at the same time. And if you then look at these materials, for instance, at stable temperatures of 600 C, so also checking catalyst stability, we see that some of them, especially this one on the right, has a very interesting profile. So it's quite stable in its performance, both for CO2 and propane conversion. So in red is CO2. And the selectivity in the hydrocarbon phase for propylene is also very high. So this was quite unexpected. We've also checked some small pore zeolites, as that is a specialty of my group. We make custom zeolites by design. What we have here is two different zeolites, two different materials tested on small pore zeolites, and we have CO2 conversion, which is on the left lower than the propane conversion, but on the right we found also materials where the propane and CO2 conversion is almost equimolar. Now both of these materials, we tested them at different reaction pressures, still show interesting behavior, and even let's say in long-term stability tests at one temperature, for instance 600 degrees C, we see very interesting behavior. For instance, here we have a very stable and equimolar conversion of CO2 and propane at a high hydrocarbon selectivity, and for this one with a really interesting profile, we convert a lot of propane, also a lot of CO2, and the performance is very, very stable. In Ghent, our partners have, instead of looking at different metals on the same support, let's say, they've looked at support interactions for gallia. They found very interestingly for gallia on ZSM5 that if they add CO2 to the reaction mixture, the activity is boosted a lot. So the propane conversion goes up really by a lot. But also at the same time, the selectivity to coke and the deactivation rate is much lower when they co-feed CO2 for these ZSM5 systems. So that is quite interesting. And of course, for all of them, a lot of characterization has been done. Specifically in the case of gallia, they have found some interesting gallium plus signals in pyridine IR, but it doesn't look like the gallia is really converting the CO2, but it still has a lot of benefits on the conversion of propane. This gallia plus signal could point to some monoatomic ion exchanged active site in the zeolite. To conclude, we did PDH plus CO2 conversion at the same time. We hope to couple them via the direct mechanism. LCA seems to point to significant CO2 reduction potentials. We performed a broad screening and that's led to very interesting discoveries on alumina, but also on small pore zeolites. We found unexpected benefits for hosting certain metals and metal oxides that are really stable and really selective. And we think the small pore zeolite is preventing coke from happening and also preventing some side reactions from occurring. In Ghent, they have discovered beneficial effects of CO2 on gallia on ZSM5 systems. So thank you for your attention.
In work package 3, the conversion of CO2 to carbon monoxide is investigated by means of electrocatalysis. For this purpose, a reactor of the kind shown here is used, where you can see two compartments separated by an ion-selective membrane. In the cathode compartment, or the compartment at the left, the reaction of interest, or the reaction of CO2 to CO is occurring, while at the anode, the oxygen evolution reaction takes place. This process can and will be driven by renewable energy. And in this project, we want to make it more economically relevant by improving the overall stability of the system, as activity and selectivity are already close to application values. We will do this by looking into the catalyst design, where we will mainly focus on silver-based catalysts, and at the reactor design by incorporating our catalysts in a so-called gas diffusion electrode to improve CO2 availability. This work is performed as a collaboration between LCAT, Cocoon, and Vito. Our first deliverable is to develop a catalyst with a minimum stability of 1 week with a loss in performance of less than 10%. For this purpose, we will pursue two pathways. In the first pathway, where LCAT takes the lead, we will utilize doped ordered mesoporous carbons as support for silver and or nickel nanoparticles. As opposed to the bare metal nanoparticles, these supports are expected to ensure a faster transport of reagents and products to and from active sites, thereby enhancing activity and selectivity, and in addition, we expect an enhanced stability of the material by anchoring the silver in a confined space and binding it with the dopant elements. In the second pathway, where Cocoon takes the lead, we will combine the advantages of covalent triazine frameworks, CTFs, with those of carbon nanotubes, CNTs, to achieve a highly conductive metal-free electrocatalyst with high surface area and nitrogen content for a stable production of CO. Ultimately, it is also planned to incorporate the silver nanoparticles prepared at LCAT in these CTF at CNT supports in a combinatorial approach. As for the first pathway, we have successfully obtained both the supports and the silver nanoparticles, as can be seen in these images, and combined them together to obtain the so-called metal-containing NOMCs. These materials still need to be evaluated in a flow cell setup, as we have noticed that testing in batch cells yields low selectivities as a consequence of the limited CO2 availability. The metal-free electrocatalysts, on the other hand, show a good selectivity in batch, but unfortunately only reach low current densities. The best results have thus far been achieved for the combinatorial approach, where we managed to reach selectivities of around 90% at 100 milliamps per square centimeters. Prolonged stability tests are currently ongoing, but initial 24-hour experiments seem promising. So to conclude, for our first deliverable, we believe we are on track to reach it, as we now need to perform the stability tests on the most promising materials. Our second deliverable is the production of a lab-scale electrochemical reactor for the production of CO. For this, we are looking into the overall process design. As mentioned in the beginning, we are looking into the incorporation of our catalysts in a gas diffusion electrode, because this allows us to let CO2 come from the gas phase, thereby increasing its availability and such also the productivity. For this purpose, we will use the proprietary gas diffusion electrodes and the production facilities at Vito. Once incorporated, we will then look at ways to improve the stability by gaining insight in electrocatalyst and electrode degradation. In a final step, we will perform a system-level optimization where we aim at decreasing the overall cell resistance by looking into and optimizing the contacts between the different parts in the cell. As such, we hope to increase the overall process efficiency. Finally, also the possibility to stack several cells together is being evaluated to further improve productivity. Here, we currently did some tests with an alternative non-optimized nickel-based catalyst in our flow electrolyzer. These tests already seem quite promising as we achieve similar performances as commercial silver nanoparticles at current densities of up to 200 milliamps per square centimeter with a much lower amount of metal. These materials also seem to be stable for at least 8 hours, suggesting that the developed reactor is suitable in our quest to reach deliverable 3.2. We will of course further evaluate the stability for longer periods and include our optimized electrocatalyst in this setup. In an attempt to further improve the stability of the process, Vito is simultaneously developing a novel catalyst integration method for which a patent is filed. So as to conclude on deliverable 3.2, we believe we are on track as our reactor design is complete but needs to be further utilized for extended stability testing.
Good afternoon, my name is Sami Verbrugge and I will briefly guide you through the status of work package 4 on photocatalytic CO2 to CO conversion. This is a collaboration between two research groups of the University of Antwerp, the Duel research group of Sylvia Leenaerts and myself, and the Latka research group of Peggy Cole, together with the University of Hasselt, the IMO-IMOMEC group of Anne Hardy and Marlies van Baal. And throughout the project, we also continued on a spontaneous collaboration with TNO Eindhoven in the Netherlands with a group of Pascal Busquets. I will start this overview with a quick introduction on the topic. So the basic point of our work package is photocatalysis. So this is a process where we involve materials that are activated by light. So ideally this would be sunlight to initiate a chemical reaction that is mainly initiated through the formation of electron-hole pairs. Now the main drawback of conventional photocatalysts and also the main target that we want to address during our research in this work package is that most of these common photocatalytic materials are only activated by ultraviolet or UV light, which accounts for at most 4 to 5% of the entire solar spectrum, which is fairly limited. So our main goal is to enhance this solar light response. The way that we intend to increase this solar light response is by modifying these photocatalysts with noble metal nanoparticles, which display a specific phenomenon called plasmon resonance, which in fact is basically that these metal nanoparticles act as tiny antennas for light. So in this way, we can extend the activity window of traditional photocatalysts from the 4 to 5% of UV light to nearly the entire UV visible light region, which account for almost half of incident solar light on Earth. This is also the results that you can see in the figure in the slide, whereas for typical photocatalysts like plain titanium dioxide, you only absorb light in the UV region, whereas for these photocatalysts modified with metallic nanoparticles, we have a strong absorption also in the visible light region of the spectrum. Using these plasmonic metal nanostructures, we intended to investigate two distinctly different routes. The first one, covered by task 1 and illustrated on the left-hand side of the figure, is where we use these plasmonic nanoparticles to modify traditional semiconductor photocatalysts. So in this way, these plasmonic nanoparticles, they facilitate the semiconducting photocatalytic reactions, which we conduct under ambient reaction conditions, so ambient temperature, ambient pressure, and also under realistic conditions of irradiation using simulated solar light covering the irradiance of one sun intensity. A second task, and illustrated on the right-hand side of the figure, is where we mix these plasmonic metals with catalytic metals to actually directly catalyze the CO2 to CO conversion over metal catalysts. These reactions are carried out under more stringent reaction conditions, elevated pressure up to 2.5 bar, and at elevated temperature around 150 degrees Celsius. For this, we also use higher irradiance levels up to the equivalent of 20 suns. For both approaches, we have synthesized and screened and tested a variety of different materials and plasmonic catalysts as well, ranging from typical semiconductors like titanium dioxide, nanoparticles consisting of gold, silver, or ruthenium, metallic particles of cheaper metals like iron. We also tested copper oxide and spinel structures. We have tested those in a recirculating batch system, entirely directly in the gas phase by administering a mixture of CO2 and hydrogen as the reducing agent in helium as a carrier gas, and detected the product formation with GC. For each of these two tasks, we have predefined a specific deliverable. For the task on plasmon-mediated semiconductor photocatalysis, we have proposed a CO2 turnover of 1 micromole per gram per hour and to reach a selectivity of at least 50% towards CO. Now, through the results that we have obtained, we can proudly present that the best rate in terms of turnover towards CO was about 60 micromole per gram per hour for a 2-8% silver on titania catalyst. We were also able to reach over 95% of selectivity towards CO for two types of materials that were tested, consisting of gold on titania and gold ruthenium bimetallic particles on titania. It's good to mention that these key performance indicators that we have obtained are actually amongst the state-of-the-art values that we can find in current recent literature. Now, in comparison to other technologies, these turnover frequencies, they might seem rather low, but it should be considered that we only use sunlight as an energy input. So we do not put in any other electrical bias, no elevated temperature or pressure in these specific reaction conditions. And still, we obtain an excellent selectivity, which is still improving as we go along. The second deliverable commensurate to the task of direct plasmon-assisted catalytic conversion on metals, that we propose higher turnovers of CO2 up to 0.05 moles per gram per hour at 35% of CO selectivity. Now, these experiments, they are still ongoing in the final months of the project. This finally brings me to the outlook, the opportunities, and a reflection on the realistic applicability of this photocatalytic CO2 to CO conversion in practice. Now, if you consider that with traditional semiconductor photocatalysis, you can have CO2 conversion to CO with a space-time yield of less than 1 kilogram per square meter per year, which is fairly low. And you can calculate that by involving these plasmonic nanostructures, you can increase the space-time yield roughly by a factor of 10,000 to up to 29 kilograms per square meter per day. So in that sense, it actually enables a very realistic implementation in practice to treat small to medium CO2 point sources emitting less than 1 megaton per year. You should also consider that with this plasmon-mediated photocatalytic technology, you actually require zero energy input as long as the sun is shining. Of course, sun is not shining all the time, which still makes photocatalysis a very promising complementary technology that you can apply everywhere you have a sunny period. Now, further opportunities for further research definitely involve to continue the search towards stable photoactive materials, but also to study this in conjunction with photoreactor design, because that will also determine to a very large extent the overall efficiency of the process. If you have any further questions or comments in this regard concerning this fourth work package, please contact me at all times. Thank you for your attention.
I'm Annemie Boogaerts, head of the research group Plasmans, and I will be presenting the results of work package 5 on plasma and plasma catalysis, and specifically task 5.1 on improving gliding arc plasma reactor design. This is our existing gliding arc plasma reactor, consisting of an anode, a cathode, tangential inlets, and the arc in the center. Showing a picture of the plasma and results of our fluid dynamic simulations, showing the gas flow pattern with an outer vortex to the tangential inlets and an inner vortex going to the outlets. And this shows the calculated arc, which is stabilized in the center due to the flow. and ideally all the gas passes through the arc plasma for efficient gas conversion. However, we see that only a fraction of the gas is passing to the arc, and this is limiting the conversion. So we need to do reactor design improvements. For that reason, we developed 5 combined models for gliding arc reactor design improvements. So this shows the reactor design with the inlets and the outlets. The first model is a 3D turbulent flow model to calculate the gas flow. Then we developed a 3D thermal plasma model for the arc movements, followed by a 2D non-thermal plasma model for a more accurate arc temperature. And these models give us the 3D plasma parameters, based on which we can calculate quasi 1D simulations to calculate the chemistry. And the link between both are particle tracing simulations for the molecule trajectories to know the parameters along the molecule trajectories which we need to do the quasi 1D simulations. And based on this model, we developed an improved reactor design where the vortex flow, so you see here the flow pattern, and the vortex flow pushes the arc inside the plasma, inside the taper, so all the gas passes through the plasma and there is improved conversion. And this shows results for 2 different taper radii of 2 millimeter and 4 millimeter. And we see that the one with 4 millimeter leads to a higher conversion and a higher energy efficiency. And the values we obtained of 60% are really very good values. They are even record values. Thank you for your attention.
Good afternoon. My name is Vera Meijner from the University of Antwerp, the Laboratory of Adsorption and Catalysis, where we study synthesis property performance correlation in different type of applications such as catalysis. So task 5.2 is a feasibility task which is done together with Annemie Bogaerts that you just heard and Vladimir Galvita from the University of Ghent. Task 5.2 is a feasibility study of integrated different conversion processes in one process adjusted to each other in order to further enhance its potential. As discussed by Professor Bogaerts, the gliding arc plasmatron does not convert all of the CO2 into CO because not all of the gas passes through the arc. Moreover, the exhaust of the gliding arc plasmatron is a hot gas stream because the gliding arc plasmatron produces quite a lot of heat. We have measured this heat, and at about 1 centimeter from the exhaust, the temperature is still around 800 degrees C. So what is the concept that we want to study? This is to integrate a packed bed just behind the gliding arc plasmatron, and we can use it at different heights. This is an old tube that you see here. We have a new design of the reactor tube, which is behind here, to have different possibilities to put a packed bed. So the packed bed can be put at different positions with different heights and of course with different materials and different shapes in order to integrate 2 processes. So the gliding arc plasmatron produces a mixture with partially converted gas and heat, and the heat will be recovered on the packed bed behind the gliding arc plasmatron and do a further conversion of the gas. In this case, in case of D2M, we further convert it to CO with a target of 90% conversion, which should be feasible with the temperatures of the exhaust stream. Important, we are not supplying extra energy, we are using the energy of the gliding arc plasmatron to heat the bed. Of course, there's also potential for other processes. We are now converting the CO2 further to CO, but if you would, for example, have a mixture of syngas at the exhaust, you could also do a further process where you would convert the syngas to something else. So there's more potential than the one that we are now studying in D2M, where we try to make CO as pure and with as high conversion as possible. Now, what are the challenges we are facing? So why are we doing a feasibility study? Well, of course, the plasma exhaust is a different composition than what you normally would use on a thermal process. Yeah? Also, the energy source, so the recovery of the heat, we have to make sure that this is balanced that these two are balanced, so that the operation of the gliding arc plasmatron, its gas composition, its heat, is matching with the packed bed that we are putting behind. Secondly, we have to evaluate that the stability of the plasma stays in place when we put packing materials behind the gliding arc reactor. As we have seen from the modeling of Professor Bogaerts, this flow behavior is very important, so we have to make sure that we do not disturb this. At the moment, with results we have now and the catalyst and shapes we have used up to now, this stability of the plasma stays in place, and we also already found a way to manipulate the flow and conversion to some extent. So it has a positive impact up till now. We will also study the type of materials that we put inside, and we will keep this information confidential, and also the size of the bed and the distance of the bed to the gliding arc position. Why is this important? I will show you a few results of temperature measurements that we have done here in the post plasma reactor tube without the packed bed present. So there you can see the temperature of the exhaust stream when the reactor is not isolated in this case. And you can see that at 5 centimeters from the exhaust, so close is about 800, at 5 centimeters from the exhaust, at the flow rate of 10 liters per minute that we were using at that time, the temperatures can be as high as 450 degrees or lower depending on your gas composition. Now, of course, the closer you go to the gap, the higher it will be. And also when you start isolating your reactor, this will be different. But it shows how important it is to integrate both processes and to match them to each other. And this is what the feasibility study is about, how much we can influence the conversion towards CO by having a smart combination of these two processes. Thank you.
Hello everybody, my name is Evangelos Delikonstantis and I'm going to talk about nanosecond pulse discharge-driven CO2 splitting. Over the past 6 months we have worked on plasma experimental setup. Today the setup looks like this. It comprises 3 basic parts: the gas supply system, the analytic part, and the plasma reactor with the respective peripherals, as you can see on the left. A plate-to-plate plasma reactor has been designed and built for CO2 splitting experiments. A nanosecond pulse power supply was employed to power the reactor and initiate the non-thermal plasma. The key characteristic of this new power supply is the very steep voltage rise rate of the pulse, which mainly forces the electrons to accelerate along the applied electric field. As a result, high electron energy and density are attained inside the plasma, which consequently enable electron-induced CO2 dissociation reactions. A short parametric study aiming at the highest CO2 conversion has initially been performed, varying different parameters, as you can see on the slide, all of them linked with the plasma energy density. It was concluded that plasma energy density drives the CO2 conversion rate. Further, a new nanosecond pulse power supply was employed, featuring shorter pulse duration and steeper voltage rise rate than the previous one. Overall, the channeling of electrical energy into electron kinetic energy was maximized, thereby higher energy input, higher efficiency and higher performance were attained. This is reflected by the high CO2 conversion, almost 20% per pass, and CO selectivity, which was reached up to 90% in our recent experiments. Next, we are going to apply chemical looping approach in order to further increase the carbon monoxide yield per single pass. Based on the literature, almost 100% carbon dioxide conversion is attained in the plasma when such nanosecond pulse plasmas are employed. But the undesirable reaction of partial oxidation of carbon monoxide back to carbon dioxide is also favorable at this operating window. Via chemical looping, we intend to capture the excess of oxygen radicals in order to block this backward reaction. There are more exciting things to come, so stay tuned. Thank you very much.
Work package 6 of the D2M project focuses on the super dry reforming process. The super dry reforming process is a chemical looping process which allows to selectively transform methane and carbon dioxide into carbon monoxide. The global reaction equation shows that up to 3 molecules of carbon dioxide can be converted into carbon monoxide at the cost of hydrogen being converted into water vapor. In the first step, a catalyst is used to transform methane, carbon dioxide, iron oxide and calcium oxide into water vapor, metallic iron, and calcium carbonate. During the second step, the reduced iron and carbonated calcium oxide are regenerated isothermally by applying an inert sweep gas. This sets in motion the decomposition of the calcium carbonate into calcium oxide and CO2, which is converted into CO upon reoxidation of iron into iron oxide. By using this two-step procedure, the production of water vapor and carbon monoxide is separated. The water-gas shift reaction, in which CO and water react with formation of CO2 and hydrogen, is circumvented by using this two-step approach. One possible reactor configuration for carrying out the super dry reforming process in a permanent periodic regime comprises the use of multiple parallel fixed bed reactors with switching valves, as illustrated on this slide. A pilot unit with an anticipated capacity to convert 1 kg of CO2 per hour will be commissioned at the LCT in 2022. A techno-economic assessment has shown that the conversion of biomethane and carbon dioxide into carbon monoxide has the potential to be economically viable at CO prices between 180 and 320 euros per ton. Starting from biogas directly, if available on site, could be even more beneficial as biogas already contains part of the carbon dioxide feedstock required in the super dry reforming process. The looping materials are a critical component of the super dry reforming process. The most important performance metrics are the gravimetric exchange capacity of oxygen and carbon dioxide, the selectivity towards products at specific reaction conditions, and the stability over thousands of cycles. On the other hand, the availability and cost of the materials plays a major role when considering the scale-up of this process to a meaningful level. Ideally, cheap and abundant sources of metal oxide should be used. In what follows, some innovations regarding the looping solids will be illustrated. A large set of materials was synthesized using different kinds of methods. Each colored quadrilateral on the graph corresponds with one such material, while the four axes correspond with the gravimetric CO2 sorption capacity, CO2 desorption capacity, hydrogen oxidation capacity, and CO2 reduction capacity, all of which are relevant for the super dry reforming process. It can be seen that it was possible to synthesize multifunctional materials comprising all the required functionalities on the nanoscale. This graph shows the corresponding temperatures at which the maximum reaction rate occurred for each of these material reaction combinations. A broad spread is found, meaning that the working temperature of the process can be optimized by choosing an adequate material formulation. Besides materials synthesized in our lab, we also did some preliminary tests on an industrially sourced material which underwent limited additional treatment. The results are shown in red on this slide. The left graph shows the hydrogen oxidation rate during temperature programmed reduction, while the right graph shows the CO production rate during temperature programmed reoxidation. These results show that it definitely seems worthwhile to look into sourcing industrial metal oxide containing materials. In conclusion, the material formulation and synthesis method have a great impact on the functionality of the materials and the operating conditions of the super dry reforming process. In the following months, the focus will be on stability testing as well as further exploring the possible usage of industrially sourced materials.